At the threshold of sleep, when the body grows heavy, the eyelids seal shut, and thoughts scatter into disconnected fragments, a sudden shock arrives without warning. The entire body convulses, the legs kick out, the arms fling wide, and the heart pounds violently. Suddenly, you are fully awake, gripping the sheets with the overwhelming sensation that you are falling off a step, through a floor, or from something tall. The fall lasted less than a second, yet the physical certainty that it was real, that you were plunging through empty space, carried a conviction no conscious thought could ever manufacture. You never moved from the bed. The fall unfolded inside the brainstem rather than in the room, and the emergency response that triggered a full-body extensor contraction designed to save you if you had actually been falling is the swiftest motor reaction the human body can produce. 80 milliseconds from detection to muscle activation. Quicker than a deliberate reach, quicker than pulling away from pain, quicker than the blink of a startle response. That speed exists because the ancient challenge that shaped the reflex required it. Grabbing a branch mid-fall from a sleeping perch demanded action before the drop carried the body beyond arm's reach. 80 milliseconds. Survival dictated that narrow margin. Your brainstem executed it in under 80 milliseconds. The real question is why the brainstem believed you were falling while you rested peacefully on a flat surface in a dark bedroom. The answer travels through a gravity sensor inside your inner ear that never powers down, a motor shutdown requiring 15 minutes to finalize, and a detection algorithm that has been operating for 60 million years of primate evolution, calibrated for a problem the human body resolved 2 million years ago when it descended from the canopy. The brainstem does not know you climbed down. Each night, at the edge of sleep, it performs the check. What exactly is this gravity sensor, and why does it continue running as sleep takes hold? Within each inner ear, tucked behind the cochlea, sit two tiny structures known as the otolith organs, the utricle, which senses horizontal motion, and the saccule, which senses vertical motion, including the constant downward pull of gravity itself. Each organ houses a sensory patch called a macula, a layer of hair cells crowned by a jelly-like membrane studded with calcium carbonate crystals known as otoconia. These crystals are dense, roughly 2.7 grams per cubic centimeter, nearly triple the density of the surrounding endolymph fluid at about 1 gram per cubic centimeter. That density gap is exactly what allows the system to function. Under gravitational force, the heavier crystals feel a stronger downward pull per unit of volume than the lighter fluid encasing them. The crystals shift against the fluid, and this relative motion is what the hair cells register. If the crystals matched the fluid's density, gravity would tug on both identically, no shifting would occur, and the sensor would be entirely blind to orientation. The whole apparatus relies on the density difference between the mineral crystals and the biological fluid holding them. Gravity draws the denser crystals down relative to the fluid. They pull the gelatinous membrane along with them, and the membrane bends the stereocilia of the hair cells, those microscopic hair-like projections perched atop each cell. This bending opens mechanotransduction channels through delicate structures called tip links, thin filaments connecting the top of each shorter stereocilium to the side of its taller partner. When the stereocilia tilt toward the taller side, the tip links yank open ion channels at their anchor points. Potassium and calcium ions flood through, the hair cell depolarizes, and a signal races along the vestibular nerve, reaching the brain stem within milliseconds. That same exact mechanism operates in the cochlea. Stereocilia bending, tip links opening ion channels, hair cells depolarizing. Same physics, different organ, different message. The cochlea perceives sound frequencies through vibrations relayed from the eardrum, while the otoliths perceive gravitational acceleration through the weight of calcium carbonate crystals dragging on a membrane. One organ listens the other ways. Both employ identical molecular machinery to convert a mechanical force into an electrical impulse the brain can interpret. Gravity confirmation runs uninterrupted every second, awake and asleep. The report it delivers to the brain stem carries a simple message. You are upright. The crystals are pulling at their expected angle. You're not falling. This confirmation persists throughout the night, across every sleep stage, through every dream, through every shift between light and deep sleep. The otolith crystals maintain their gravitational drag. The hair cells keep transducing, and the vestibular nerve keeps delivering the orientation update. The gravity sensor never shuts off because the brainstem never stops requiring the information about which direction is down. This is how you keep your place on the mattress during sleep, how you avoid rolling off the bed after hours of unconsciousness, how the body maintains its spatial bearing throughout a night of complete motor suppression. The vestibular system runs independently of consciousness, independently of muscle tone, independently of visual input, supplying the gravitational reference the brainstem needs regardless of what any other sensory system is doing. Gravity detection stays online, but something else shuts down during the slide into sleep, and that shutdown produces a signal the gravity sensor cannot interpret. Sleep onset is a gradual transition spanning 5 to 15 minutes, not a switch that flips instantly. Sapper and colleagues mapped the mechanism in nature. The ventrolateral preoptic area of the hypothalamus releases inhibitory neurotransmitters, gamma-aminobutyric acid and galanine, which progressively suppress the reticular activating system in the brainstem. The reticular activating system is the arousal engine. As this inhibition strengthens, muscle tone declines through the descending suppression of spinal motor neurons that sustain postural tension. The muscles that kept your body upright all day, the leg extensors, the trunk stabilizers, the arm flexors, begin releasing their contractions as the inhibitory signal reaches each motor neuron one circuit at a time. Minutes, not seconds. During this transition window, inhibition remains incomplete. Some motor pathways have already been silenced while others still hold partial activity. Muscle tone collapses unevenly throughout the body, and the proprioceptive system reports a shifting postural landscape that changes moment by moment as different muscle groups let go at different rates. The large postural muscles of the legs may release before the smaller stabilizers of the trunk. The shoulder girdle may still hold tension while the hip flexors have already quieted. The brainstem then receives a proprioceptive report that contradicts itself internally, with some areas signaling stable tone while others signal collapse, a pattern that resembles the uneven grip failure of a primate whose hands are slipping from a branch at different speeds, rather than the uniform relaxation of a body sinking peacefully into a mattress. Sensory processing enters the hypnagogic state, that borderland between waking and sleeping where imagery fragments, spatial perception warps, and coherent thought dissolves into loosely linked associations. At this point, three systems report to the brainstem about the body's position in space. The vestibular system, the otolith gravity sensor, continues operating uninterrupted through the transition. The proprioceptive system, the network of sensors and muscles and joints that reports body position and muscle tension, is collapsing as the motor inhibition advances. And the visual system is offline, the eyes closed, offering no spatial reference at all. Three inputs, two of them fading, and a brainstem algorithm that must judge in real time whether the body is safely drifting off or dangerously plunging. What does the brainstem do with this pattern? Integration of the three inputs governs postural stability, running a continuous calculation that measures what each system reports against what the others confirm. During waking hours, all three inputs align, and that agreement is what the brainstem reads as safety. The otoliths report stable gravitational orientation, confirming which way is down with sub-second updates. The proprioceptors report stable muscle tone and joint position across every muscle group, confirming that the body is supported and posture is preserved. The visual system verifies the body's orientation in space through optic flow patterns and spatial cues, the eyes tracking continuously. When all three channels concur, the brain stem sustains postural tone and no emergency reflex activates. Agreement is the signal indicating you are safe. Disagreement is the signal that means evaluate for a fall. At sleep onset, that agreement collapses. Proprioceptive input fades as muscle tone drops. Muscle spindles, the stretch receptors embedded inside the muscle fibers themselves, continuously report muscle length to the brainstem. During normal waking posture, these spindles fire at a steady baseline that the brainstem reads as stable tone. During sleep onset, the descending inhibition silences the motor neurons, and the muscles lengthen as tension releases. The spindle discharge rate falls quickly as the muscle extends passively. That specific pattern of rapidly declining spindle discharge is nearly indistinguishable from the pattern spindles produce during an actual free fall, when the muscles extend under gravitational acceleration because the body has lost support. The brainstem cannot separate the proprioceptive signature of voluntary muscle release during safe sleep onset from the proprioceptive signature of involuntary muscle extension during a fall, because both generate the same signal, rapid decline in spindle firing rate across multiple muscle groups at once. Visual input is missing, eliminating the confirmation that would normally settle the ambiguity. Vestibular input keeps reporting stable gravity, but the vestibular signal alone cannot override the pattern the other two inputs are generating. A postural algorithm refined across 60 million years of primate evolution runs a simple conditional. If muscle tone drops abruptly and visual confirmation is absent, and the body was recently oriented vertically, then the most probable cause is loss of grip. The primate is falling from the sleeping branch. The algorithm cannot factor in the probability of a bed because the algorithm predates beds by roughly 59,995,000 years. It cannot weigh the evidence of a pillow, a mattress, or a darkened bedroom because none of those objects existed during the evolutionary timeline. The detection circuit was sharpened through natural selection in an environment where sleep always happened at height, where every sleeping primate was one loosened grip away from a fall that could kill it, and where sudden muscle relaxation during sleep always meant the grip had failed and the descent had begun. A whole body extensor contraction fires, legs extending, arms flinging outward, trunk stiffening, exactly the pattern that would have snagged a branch or a neighboring limb during a plunge from height. The reflex arc travels from a vestibular nucleus through the lateral vestibulospinal tract to the spinal motor neurons, activating the anti-gravity extensors in all four limbs simultaneously. Latency under 80 milliseconds from mismatch detection to muscle contraction. The contraction pattern is tailored specifically for catching. The arms extend and abduct, reaching outward toward whatever surface might halt the fall. The legs extend against gravity, bracing for impact or pushing toward support. The trunk stiffens, preventing the body from folding at the waist during the deceleration a catch would produce. Every component of this motor pattern maps precisely onto the mechanical demands of arresting a fall from height, a pattern that would make no functional sense as a reaction to lying in bed, but makes complete functional sense as a reaction to falling from a tree. It is the fastest motor response in the body, faster than any voluntary action the cortex could launch, because the cortex is not involved. The reflex operates subcortically beneath conscious awareness, executing before the thinking brain receives any information about what occurred. By the time the cortex processes the arousal signal and conscious awareness returns, the reflex has already completed its motor program. The arms have already extended, the legs have already kicked, and the heart rate has already surged. You become aware of the jolt only after it is finished. The conscious experience of a jerk is the cortex receiving a report of an event the brainstem has already dealt with, in the same way you become aware of pulling your hand from a hot surface only after the spinal reflex has already retracted it. I experienced the jolt differently the first night after I learned about the 3-input mismatch. The arms that flew outward were reaching for a branch. The legs that kicked were bracing against a trunk. The whole body extension pattern was the geometry of a primate catching itself mid-fall. And the brainstem that fired, it was executing an ancestral evaluation that had not updated its environmental model in 2 million years. The reflex fired, the body jerked, and then the image arrived. Did the falling dream cause the jolt, or did the jolt cause the falling dream? You remember it the other way around. You remember falling and then jerking. Memory places the image of falling before the reflex, as though the vision triggered the jolt. The sensation felt so vivid, the curb, the cliff edge, the staircase dropping away, that the causal order seems self-evident. The dream caused the reflex, but the chronology runs in the opposite direction. The vestibulospinal reflex fires in under 1/10 of a second, a subcortical preconscious event the visual cortex has not yet participated in. The reflex execution sends an arousal burst through the reticular formation. The visual cortex, already in the hypnagogic state and producing fragmented imagery without waking coherence, receives the arousal signal and generates a brief falling scene. A curb, a cliff, a floor giving way, imagery consistent with the motor pattern the body has just executed. Conscious awareness returns. The brain encounters two events, a falling image and a body jolt, and assembles them into the narrative that makes causal sense. The fall caused the catch. Chronologically, the image came after the reflex. The brain reversed the order to build a coherent story from events that unfolded in the opposite sequence. This retroactive assembly is a documented feature of cortical processing. The brain routinely constructs causal narratives from temporally scrambled inputs, placing causes before effects even when the neural processing occurred in the reverse order. The mechanism runs through the same retrospective coherence system that makes you perceive a touch on your hand as simultaneous with the visual confirmation of being touched, even though the tactile signal from the hand reaches the cortex tens of milliseconds before or after the visual signal, depending on distance. The brain stores both signals in a brief temporal buffer and assembles them into a single coherent experience with the cause preceding the effect regardless of which signal arrived first. The jolt triggered the falling dream. The visual cortex, having received the arousal burst from the reflex execution, produced the most contextually appropriate image it could gather from the hypnagogic fragments already circulating, a scene of falling. That scene fits contextually because the motor pattern the body just performed was a catching response, and the cortex, working backward from the motor output, generated the sensory experience that would normally precede such a response. The visual cortex was recruited after the reflex executed, producing an image that the waking brain retroactively positioned as the cause rather than the consequence. The sequence evidence supports this temporal reversal, consistent with hypnagogic imagery research and the established latency gap between subcortical reflex execution and cortical image generation. The reflex completes within the catch interval. Cortical image generation requires at least 150 to 200 milliseconds. The reflex finishes before the image begins forming. The causal direction the memory reports is the opposite of the causal direction the timing requires. So the reflex fired because the falling assessment computation detected a mismatch. The image arrived because the cortex was recruited after the reflex. The question then shifts. Why does the reflex fire more on certain nights than on others? The answer runs through three conditions that each influence the transition window, that 5 to 15 minute stretch where the brainstem conditional is most susceptible to the mismatch. Caffeine first. Adenosine accumulates during waking hours, steadily building sleep pressure. Caffeine occupies the adenosine receptors without activating them, physically blocking adenosine molecules from binding. The sleep pressure keeps mounting. Adenosine keeps being produced, but the receptors that would translate that pressure into the inhibitory cascade cannot receive the signal because caffeine molecules are lodged in the binding sites. Caffeine has a half-life of roughly 5 to 6 hours in most adults. A coffee consumed at 4 in the afternoon still occupies about 50% of adenosine receptors at 10 in the evening. The receptors are half-blocked when the transition to sleep begins, meaning the inhibitory cascade driving that transition must work against a background of stimulant occupancy that delays and stretches the process. Once the caffeine is eventually metabolized and cleared from the remaining receptors, the built-up adenosine rushes in, and the transition that was postponed now begins against a higher baseline of sleep pressure than would have existed without the caffeine. When caffeine wears off and the transition finally begins, the inhibitory process unfolds against a background of residual stimulant effect. The transition stretches. The window of incomplete motor inhibition widens. More time in the vulnerable state means more opportunities for the proprioceptive collapse to reach the pattern the detection circuit reads as a fall. The coffee you drank at 4 in the afternoon widened the transition window at 11 at night. Next, sleep deprivation. When homeostatic sleep pressure runs very high, the accumulated adenosine drives the transition more abruptly. Once it starts, muscle tone drops faster and more thoroughly. The proprioceptive collapse becomes sharper, a signal that more closely resembles the sudden grip loss of an actual fall than the gradual drift of a normal transition. The brainstem interprets that sharp collapse as a higher confidence fall detection. The exhausted brain plunges into sleep faster, and the faster collapse looks more like the real thing to the ancestral computation evaluating the input pattern. The rate of proprioceptive change is what separates a gradual transition from a sudden one. A slow decline in spindle discharge over 15 minutes reads as safe drift, while a sharp decline over 3 to 4 minutes reads as an abrupt release that the brainstem cannot distinguish from a grip failure at height. Then comes stress. Elevated sympathetic tone during the transition keeps the reticular activating system partially engaged while the ventrolateral preoptic area attempts to suppress it. The body drifts toward sleep, snaps back toward waking, drifts again, snaps back. Each oscillation produces a partial proprioceptive collapse followed by partial recovery. The brainstem receives repeated approach to threshold signals, each one echoing the beginning of a fall. Multiple opportunities for the mismatch to trigger. The stressed brain oscillates through the transition, and each oscillation presents the falling detection evaluation with a fresh pattern to weigh. If you're exhausted, stressed, and caffeinated, you carry the longest transition window, the sharpest proprioceptive collapse, and the most oscillation all at once. The hypnic jerk fires multiple times before sleep finally consolidates. Those multiple jolts across a single transition are multiple false alarms from one brainstem calculation evaluating the same mismatch under the worst possible conditions. Disrupted transitions produce more firings. But the reflex fires at all because of where primates once slept and how long the brainstem remembers. Why does the reflex persist when the problem it's solved no longer exists? Primates have slept in trees for approximately 60 million years. Chimpanzees, orangutans, and gorillas construct sleeping platforms in the canopy every night, choosing branches for structural integrity, weaving smaller branches into a stable mat, bending larger branches inward to form a rim, and positioning the finished nest 10 to 30 meters above the ground, a height from which a fall onto hard forest floor would produce skeletal injuries incompatible with continued survival in a competitive social group. Construction takes 5 to 20 minutes and is performed fresh each evening, an investment of time and energy that reflects the seriousness of the fall risk the sleeping platform mitigates. A chimpanzee that built a poor nest and fell during the night sustained injuries that reduced its reproductive fitness. A chimpanzee that built a secure nest and possessed a fast-catching reflex as backup survived falls the nest failed to prevent. Goldberg and colleagues described the vestibular system's role in postural reflexes across primate species, documenting that the vestibulospinal reflex pathway is preserved across every primate lineage studied. The arboreal, sleeping environment placed extreme selection pressure on the falling detection circuit. The primate that caught the branch survived the night. The primate that missed fell 10 to 30 meters onto the forest floor. The reflex needed to be fast, under a tenth of a second, because the fall accelerates under gravity and the branch slips out of reach within 200 milliseconds of grip loss. It needed to be whole body, all four limbs extending simultaneously because the primate could not predict which limb would reach the branch first. And it needed to be pre-conscious, firing before the cortex could process the situation, because conscious evaluation takes 150 milliseconds, and by then the branch is already gone. Hominins transitioned to ground sleeping approximately 2 to 3 million years ago with the emergence of Homo erectus and the mastery of fire, which provided predator deterrence that made ground sleeping survivable. 2 to 3 million years represents roughly 3 to 5% of the selection window, during which the reflex was under selection pressure. The reflex remains in the brainstem because the evolutionary pressure that would remove it, a fitness cost from jerking on a flat surface, does not exist. The jolt is harmless. It wakes you briefly. Your heart pounds for 10 seconds and sleep resumes. There is no selection against a reflex that carries no cost. Evolution removes traits through negative selection pressure, a fitness disadvantage that makes carriers less likely to reproduce. A reflex that wakes you briefly, accelerates your heart for 10 seconds, and allows sleep to resume within minutes carries no measurable fitness cost. The brief arousal does not degrade sleep quality across the night. The heart rate surge does not damage the cardiovascular system. The momentary fright produces no lasting psychological harm. Without a fitness cost, the negative selection pressure required to erode the circuit simply does not exist. In 3 to 5% of the reflex's evolutionary history, the interval since ground sleeping began has produced no measurable reduction in the reflex's prevalence or sensitivity. Oswald documented the phenomenon in Brain in 1959, and Broughton classified it among the normal motor events of sleep onset in 1988. The hypnic jerk is a normal brainstem reflex that generates a false positive from an input pattern that was a true positive for 58 of the last 60 million years. Electroencephalography confirms no epileptiform activity during the jerk. The electrical pattern captured during a hypnic jerk shows a normal vertex sharp wave, a transient associated with the wake-sleep transition, followed by the motor artifact of the contraction itself. No spike and wave pattern, no rhythmic discharge, no postictal suppression. The electrical signature of the hypnic jerk is the signature of a brainstem reflex, not a cortical seizure. The reflex occurs exclusively at the wake-sleep transition. Approximately 60 to 70% of the population experiences hypnic jerks at some point, with prevalence rising during periods of stress, caffeine use, or sleep deprivation. Frequency varies across individuals, ranging from occasional episodes, separated by weeks, to nightly occurrences. Some individuals experience the jerk multiple times in a single transition, the reflex firing repeatedly as the body oscillates between partial wakefulness and partial sleep before the transition finally consolidates into stable sleep. More frequent jerks do not indicate pathology. If you experience it nightly, your brain stem carries a sensitive falling detection threshold, a lower mismatch confidence level required to trigger the reflex. If you rarely experience it, your brainstem requires a stronger mismatch signal to trigger a higher confidence threshold that filters out the weaker mismatch patterns the transition produces. Both are normal variations in the threshold of a preconscious reflex that every primate carries. Variations that reflect individual differences in baroreceptor sensitivity, proprioceptive signaling strength, and the depth of the hypnagogic transition the brain produces each night. Neither variation indicates pathology. Neither variation predicts sleep quality. Neither variation requires treatment. My understanding of the closing image arrived when the evolutionary timeline collided with the falling sensation. 60 million years of sleeping in trees. 2 million years of sleeping on the ground. The ancestral evaluation, checking every night. The answer always the same. False alarm. The branch gone. The circuit persisting. The brainstem reaching. The jolt was never random. It was the fastest reflex the body produces, fired by a brainstem that read the muscle relaxation of sleep onset as the start of a fall. Gravity sensor confirmed orientation. Muscles let go. The brainstem ran the falling assessment computation. It has run across the entire evolutionary timeline. Catch yourself. The branch is gone. The algorithm remains. And every night at the edge of sleep, your brainstem reaches for a branch that has not been there